Some basic intensity transformation functions. Values of the pixels will be noted. R before processing, S after. S equals T of R. Digital values of T, typically stored in one-dimension array, plus mappings from R to S implemented via table lookups. Some basic intensity transformation functions. All curves were scaled to fit in the range shown. Image negatives. Negative of an image with intensity levels in 0, L-1 is obtained by S equals L-1 minus R. Log transformations. General form S equals C log of 1 plus R, where C is a constant and R is greater or equal to 0. Expand the values of dark pixels in an image while compressing the higher level value. Power law, gamma transformations. Basic form S equals CR gamma. C and gamma are positive constants, sometimes written as S equals C of R plus epsilon gamma to account for an offset. Examples of gamma correction. CRT, cathode ray tube devices, have an intensity to voltage response that is a power function with exponents from about 1.8 to 2.5, images darker than intended. Example: expansion of intensity level is desirable. Can be accomplished with the power law transformations with a fractional component. Magnitude resonance of image MRI of a fractured human spine. And results of applying transformations. C equals 1, gamma equals 0.6, 0.4, 0.3. Opposite example. Image has a washed out appearance. Compression of image level is desirable. Values of gamma greater than 1. Aerial image and results of applying transformations. C equals 1, gamma equals 3, 3 and 5. The basics of filtering in the frequency domain. Additional characteristics of the frequency domain. SCM image of a damaged integrated circuit. Frequency domain filtering fundamentals. Given a digital image f of x, y of size m into 1, the basic filtering equation will be as shown on the screen, where g of x, y represents filtered output images, IDFT the filtered function, and h of u, v and f of u, v. For simplification, use functions h of u, v that are centered symmetric about their center plus center f of u, v, multiplying f of x, y by minus 1 x plus y. In figure, top row represents the frequency domain filters and bottom row the corresponding filtered images. Figure A simple image, B result of blurring with Gaussian low-pass filter without padding, C result of low-pass filtering with padding. Steps for filtering in frequency domain. Given an input image f of x, y of size m into n, obtain padding parameters p and q. Typically, p equals 2m and q equals 2n. Form a padded image fp of x, y of size p into q by appending the necessary number of zeros to f of x, y. Multiply fp of x, y by minus 1 raised to the power x plus y to center its transform. Compute the DFT f of u, v of the image from step 3. Generate a real symmetric filter function h of u, v of size p into q with center at coordinates p by 2, q by 2. From the product, g of u, v equals h of u, v into f of u, v using array multiplication. Obtain the processed image as per equation shown. Obtain the final processed result g of x, y by extracting the mn region from the top left quadrant of gp of x, y. Image smoothing using frequency domain filters. All filter functions are assumed to be discrete functions of size p into q. Ideal low-pass filters. Ideal low-pass filter ILPF equals 2 minus d. Low-pass filter that passes without attenuation all frequencies within a circle of radius d0 from the origin and cuts off all frequencies outside the circle. The equation is as shown on screen. D0 is greater or equal to 0. And d of u, v is the distance between a point u, v and the center of the frequency rectangle as shown. The point of transition between h of u, v equals 1 and h of u, v equals 0 is called the cutoff frequency. An ILPF cannot be realized with real electronic components. Butterworth low-pass filters. Transfer function of a Butterworth low-pass filter, BLPF, of order n and with cutoff frequency at a distance d0 from the origin. The equation can be seen on screen. Figure A shows the perspective plot of Butterworth low-pass filter transfer function, and B, filter displayed as an image, and C, filter radial cross-section of the order 1 through 4. Gaussian low-pass filters GLPFs in 2 dimensions is represented on screen. Figure A, perspective plot of GLPF transfer function, B, filter displayed as image, C, filter radial cross-section for various values of D0. Example for Gaussian low-pass filter is represented on the screen. Figure A, original image of test pattern 688 into 688, B, its Fourier transform. The table shows the low-pass filter D0 as the cutoff frequency and n is of the order of Butterworth filter. Image sharpening using frequency domain filters. High-pass filtering. Attenuation of the high-frequency components of the Fourier transform of the image. As before, radially symmetric filters, all filter functions are assumed to be discrete functions of size p into q. A high-pass HHP filter can be obtained from a given low-pass HLP filter by the equation shown. Butterworth high-pass filters. A 2D Butterworth high-pass filter BHPV of order n and cutoff frequency 2.0 is defined as R as represented on screen. Gaussian high-pass filters. The transfer function of the Gaussian high-pass filter GHPF with cutoff frequency locus at a distance d0 from the center of the frequency rectangle is defined as shown on screen. High-pass filters. D0 is the cutoff frequency and n is the order of the Butterworth filter. The Laplacian in the frequency domain will be as shown on screen, or with respect to the center of the frequency rectangle as shown. The Laplacian image is obtained by the equation shown on screen. The enhancement of the image is achieved using h of u, v negative as shown on the screen. The Laplacian in the frequency domain will be as shown on screen. Introduction of large scaling factors. Practical solution. Normalize f of x, y to the range 0, 1 before computing the DFT delta squared f of x, y and divide by its maximum value. Unsharp masking, high boost filtering and high frequency emphasis filtering. The equations are shown on screen, where k equals 1 is for unsharp masking and k greater than 1 is for high boost filtering. Expressed in terms of frequency domain computation, the low-pass filter and high-pass filter equations are shown on screen. More general formulation is also given, where k1 is greater or equal to 0 gives controls of the offset from the origin, and k2 greater or equal to 0 controls the contribution of high frequencies. Implementation. DFT. The discrete Fourier transform DFT is the equivalent of the continuous Fourier transform for signals known only at instants separated by sample times t, that is, a finite sequence of data. Let f of t be the continuous signal which is the source of the data. Let n samples be denoted as f0, f1, f2, and so on, fk and so on, up to fn-1. The Fourier transform of the original signal, f of t, would be as shown on screen. We could regard each sample f of k as an impulse having an area f of k. Then, since the integrand exists only at the sample points, the equation will take the form shown on screen. Take n equals 10 samples and implicit periodicity in DFT. N equals 10 samples, implicit periodicity in DFT. Example of DFT. Let's consider continuous time signal f of t as shown on screen. Let us sample f of t at 4 times per second. That is, fs equals 4 Hz from t equals 0 to t equals 3 by 4. The values of the discrete examples are given by the equation shown on screen. Magnitude of coefficients are shown in the figure. Separability of the 2D DFT. The 2D DFT is separable into 1D transforms as per the representation shown on screen. The 2D DFT of f of x, y can be obtained by computing the 1D transform of each row of f of x, y and then computing the 1D transform along each column of the result. Computing the IDFT using a DFT algorithm will be as shown on screen. To compute the IDFT, compute the 2D forward DFT of f star of u, v equals mn f star x, y. Take the complex conjugate and multiply the result by 1 by mn. Note, when f of x, y is real, f star of x, y equals f of x, y. Please refer to the equations on screen. Direct implementation on the order of mn2, summations and additions required. FFT implementation, order of mn log 2 mn. The discrete Fourier transform DFT of one variable. Obtaining the DFT from the continuous transform of a sample function is represented as shown on the screen. Given a set f of x of m samples of f of t, and the DFT of f of x is as shown on screen. The inverse discrete Fourier transform, IDFT, is shown on the screen. Both forward and inverse discrete transforms are infinitely periodic with period m. Discrete equivalent of the convolution is shown on the screen. Relationship between the sampling and frequency intervals. If f of x consists of m samples of a function, f of t, taken at dt units apart, the duration of the record comprising the set f of x is t equals m into delta t. Corresponding spacing in the discrete frequency domain is delta u equals 1 by m of delta t equals 1 by t. The entire frequency range spanned by the m components in the DFT is m delta u equals 1 by delta t. Extension to function of two variables. The 2D impulse and its shifting property. Impulse of two continuous variables t and z. The representation is as shown on screen. The 2D impulse and its shifting property. The equations can be seen on the screen. Extension to function of two variables, the 2D impulse and its shifting property. 2D discrete impulse equation is shown on the screen. Shifting property. The equation is as shown on the screen. The 2D continuous Fourier transform pair. F of t, z, continuous function of two continuous variables, t and z, the 2D continuous Fourier transform pair is given by the equations which are shown on the screen. For example, obtaining the 2D Fourier transform of a simple function will be as represented on the screen. Two-dimensional sampling and the 2D sampling theorem. Sampling in 2D can be modeled using sampling function 2D impulse train as per equation shown on the screen. Multiplying f of t, z by s delta t delta z, t, z yields a sampled function. F of t, z is said to be band limited if its Fourier transform is 0 outside of a rectangle minus mu max, mu max and minus mu max, mu max. 2D sampling theorem. A continuous band-limited function f of t, z can be recovered with no error from a set of its sample if the sampling intervals are as represented on the screen, where a is an oversampled, b is an undersampled band-limited function. Aliasing in images. Example, sampling checkerboards whose squares are of size 16 into 6 pixels. Figure A and B aliasing is visually negligible, then C and D masquerade as a normal image. Anti-aliasing. Effects of aliasing can be reduced by slightly defocusing the scene to be digitized, attenuation of high frequencies before the image is sampled. Effects of aliasing generally are worse when the size of a digital image is reduced. Figure A, digital image with negligible visual image. B, result of resizing its image to 50% of its original size by pixel detection. C, result of blurring image. Moire patterns. That sometimes results from sampling scenes with periodic or nearly periodic components. In optics, beat patterns produce between two gratings of approximately equal spacing. The 2D discrete Fourier transform and its inverse, the 2D discrete Fourier transform DFT of a digital image f of x, y of size m into n is as shown on the screen. The inverse discrete Fourier transform IDFT is also shown. Frequency domain filtering. Fourier transform and frequency domain is used in image filtering. Background: Fourier series and transform. Jean-Baptiste Fourier was born in 1768 in the town of Auxerre, above midway between Paris and Dijon. Contribution for which he is most remembered was outlined in a memoir in 1807 and published in 1822 in his book La théorie analytique de la chaleur, which means the analytic theory of heat. This book is translated into English and published by Freeman in the year 1878. It says that any periodic function can be expressed as a weighted sum of sines and or cosines, Fourier series. Other functions can be expressed as an integral of sines and or cosines multiplied by a weighing function, Fourier transform. Functions can be recovered by the inverse operation with no loss of information, applications to image enhancement. Function at the bottom is sum of four functions above it. Fourier idea in 1807 that periodic functions could be represented as a weighted sum of sines and cosines was met with skepticism. Primary concepts. 1. Complex numbers. Complex number C is defined as C equals R plus Ji, where I and R are real numbers and J is an imaginary number. That is, J equals square root of minus 1. Here R is a real part of complex number and I is an imaginary part of complex numbers. Real number is subset of complex number in which I equals 0. The conjugate of complex number, denoted by C or C star, is C star equals R minus J I. Complex plane. Complex numbers are viewed geometrically as point in a plane. Values of R run along the real axis and values of I in the imaginary axis. Sometimes complex numbers are represented in polar axis. C equals mod of C into cos theta plus J of sin theta, where mod of C equals square root of R squared plus I squared. This equation represents the length of the vector extending from an origin of complex plane to point Ri, and theta is the angle between vector and the real axis. Fourier series. If f of t is a periodic function of continuous variable t with period capital T, the equations will be as shown on the screen. Impulse and their shifting property. Unit impulse of a continuous variable t located at t equals 0 will be as per the equation shown on the screen. Unit discrete impulse located at x equals 0 will be as shown on screen. A unit discrete impulse located at x equals x0, variable x is discrete, and del is 0 everywhere except at x equals x0. The shifting property will be as shown on the screen. Impulse train. Sum of infinitely many periodic impulses delta t units apart. The representation will be as shown on the screen. The Fourier transform of functions of one continuous variable. Fourier transform of a continuous function ft of a continuous variable t is as shown on the screen. Inverse Fourier transform is also shown on screen. Example is as shown on the screen. Example 2. Fourier transform of a unit impulse located at the origin is as shown on screen. Periodic function with period delta t will be as shown on screen. Convolution. Convolution of functions f of t and h of t of one continuous variable t will be as shown on screen. Fundamentals of spatial filtering. Spatial filters, also called spatial masks, kernels, templates or windows, is represented as image f of x, y tends to image g of x, y. The mechanics of spatial filtering. Filtering creates a new pixel with coordinates equal to the coordinates of the center of the neighborhood, with value equaling the result of the filtering operation. For example, linear spatial filter using a 3×3 neighborhood at any point x, y in the original image, response g of x, y of the filter will be as shown on screen. For a mask of size m star n, we assume that m equals 2a plus 1 and n equals 2b plus 1, where a and b are positive integers, odd size. The general expression of a linear spatial filtering of an image of size m into n with a filter of size m star n, the equation is shown on figure. Each pixel in W visiting every pixel in F. The mechanics of linear spatial filtering using 3*3 filter masks will be as shown on screen. Spatial correlation and convolution. Correlation. Process of moving a filter mask over the image and computing the sum of products at each location. Correlation is a function of displacement of the filter. If F contains all zeros and only one discrete unit impulse, copy of W rotated by 180 degrees, that is, correlation of a function with discrete unit impulse, which is a rotated version of the function at the location of the impulse. Convolution. The same mechanics but with a filter rotated by 180 degrees. Convoluting a function with a unit impulse, copy of W at the location of the impulse, rotate one function by 180 degrees and perform the same operation as in correlation. The correlation of a filter W of x, y with an image f of x, y is as shown on the screen. For all values of x and y so that all elements of W visit every pixel in F padded appropriately, is as shown on the screen. It is convenient sometimes to write the sum of product as is as shown on the screen, where Wk represents coefficients of an m into n filter and Zk represents the corresponding intensities encompassed by the filter representation for general 3*3 filter masks shown in the picture. Generating spatial filter masks. To generate a m into n linear filter, we need to specify m star n mask coefficients selected based on what the filter is supposed to do. Example 1. Average filter with a 3×3 neighborhood. The equations are as shown on screen. Example 2. Spatial filter mask based on a continuous function of two variables, that is, Gaussian function. Here again, the equations are shown on the screen. Histogram processing. Histogram of an image M star n with intensity levels in 0, L-1. Discrete function h of rk equals nk, where rk equals kth intensity value and nk represents the number of pixels with intensity rk. Normalized histogram P of rk equals nk by mn for k equals 0, 1, 2 up to L-1. P of rk is the estimate of the probability of occurrence of intensity level rk in the image. In normalized histogram, summation of k equals 0 to L-1 of P of rk equals 1. Histogram, basis for numerous spatial domain processing techniques, provides useful image statistics, useful for image enhancement, image compression, and segmentation. Simple to calculate in software and hardware implementations. It gives convenient summary of intensity of an image. Histogram gives more insight about image contrast and brightness. Histogram of dark image will be clustered towards a lower gray level. Histogram of bright image will be clustered towards a high gray level. The low contrast image, the histogram will not spread equally, that is, histogram will be narrow. In the high contrast image, the histogram will have an equal spread in gray level. Image brightness may be improved by modification of histogram range, H of RK or P of RK. 4 basic image types: dark, light, low contrast, high contrast, and the corresponding histogram. Histogram equalization. It is the process that attempts to spread out the gray level in an image, so that they are evenly distributed across their range. It reassigns the brightness value of an image based on an image histogram. It is a technique where histogram image is as flat as possible. It gives more pleasing results across wide range of images. Steps for histogram equalization. Histogram equalization is done by following steps. Find the running sum of histogram values. Normalize the values from step 1 by dividing by the total number of pixels. Multiply the values from step 2 by the maximum gray level value and around. Map the gray level values for results from step 3 using 1-to-1 correspondence. Goals of histogram equalization. Obtain an output image with a uniform PDF. Consider continuous intensity values. PDF of output images 0 to L-1 is a dynamic range of image. Transformation from S equals T of R, and the value of R ranges from 0 to 1. Transformation function T of R must satisfy the following condition. T of R is single-valued and monotonically increasing in the interval R ranging from 0 to 1 and T of R ranging from 0 to 1 and again R ranging from 0 to 1. Below figure says that monotonically increase the functions showing how multiple values can map to a single value. Strictly monotonically increasing function. This is 1-to-1 mapping both ways. The inverse transformation function can be defined as R equals T raised to the power minus 1 into S, where S ranges from 0 to 1. Probability density function of transformation can be written as shown on the screen. In these equations, PS of S and PR of R are known as probability density functions. PDF, probability density function. Cumulative distributive function of transformation can be written as shown on screen. Below figure shows an arbitrary PDF, result of applying transformation in an intensity level. The equations are as shown on screen. Histogram equalization or histogram linearization, discrete form. The equations are as shown on screen. Histogram equalization. For example, Take a 3-bit image L equals 8, 64 star 64 pixels. Round intensity values to nearest integer. And the representation is as shown on screen. Table for intensity distribution and histogram values for 3-bit 64 star 64 image is as shown. Below figure represents histogram equalization of 3-bit image. Original image, transformation function, equalized histogram. Histogram equalization as an adaptive contrast enhancement tool. Tends to spread the histogram of the input image. Intensity levels of the equalized image span a wide range. Contrast enhancement. Below figure shows how we can get histogram images and histogram equalization image from original image. Original histogram image, original images, histogram equalization images, histogram of figure C. Histogram matching. Histogram matching or histogram specifications R and Z are continuous intensities, random variable. PR of R and PZ of Z correspond to PDF. PS of Z is a specified PDF. We already know that dynamic range of image equals 0 to L-1. The histogram matching equations are as shown on screen. Procedure to obtain histogram matching. Obtain PR of R from the input image and use equation 1 to obtain the values of S. Use a specified PDF in equation 2 to obtain the transformation function G of Z. Obtain the inverse transformation Z equals G minus 1 into S, that is by mapping from S to Z. Obtain the output image by equalizing the input image using equation 1. For each pixel with value S in the equalized image, perform the inverse mapping Z equals G minus 1 into C to obtain pixels in the output image. Discrete formulation of histogram matching equations are as shown on the screen. In these representations, Sk is a value of histogram equalized image. Discrete formulation of the histogram specification procedure. Compute PR of R of input image and use equation 4 to obtain the values of Sk rounded to the integer range 0, L-1. Compute all values of G using equation 5 for Q equals 0, 1, and so on up to L-1 and the specified histogram values. Round the values of G to integers in the range 0, L-1 and store those values in a table. For every value of Sk, use stored values of G to find the corresponding value of Zq so that G of Zq is closest to Sk and store these mappings from S to Z. When mapping is not unique, choose the smallest value by convention. Form the histogram specified image by histogram equalizing the input image and then mapping every equalized pixel value Sk of this image to the corresponding value Zq using the mapping found in step 3. The table for actual and specified histograms is shown on screen. Here, histogram of a 3-bit image is shown, specified histogram, transformation function obtained from specified histogram, result of performing histogram combined B and D. Step 1. Obtain scaled histogram equalized values are shown on screen. Step 2. Compute all values of G rounded are shown on screen. In the table shown, all possible values of the transformation function G is scaled, rounded and ordered with respect to Z. Step 3. For every Sk, find the smallest value of Zq so that G of Zq is the closest to Sk. Step 4. Use table to map pixels in the histogram equalized image into a pixel in the new histogram specified image. Values of the resulting histogram will be: Example, comparison between histogram equalization and histogram matching. Images of Mars moon taken by NASA. Original histogram image. Sampling and the Fourier transform of sampled functions. Sampling model of the sampled function. Multiplication of f of t by a sampling function equal to a train of impulses delta t units apart. The equation is as shown on screen, where a represents a continuous function and b train of impulses, c sampled function formed with product of a and b, and d sampled values obtained by using shifting property. The Fourier transform of sampled functions, infinite periodic sequence of copies of f mu continuous. Separation between copies determined by 1 by delta t is also shown on screen. The sampling theorem. In the figure, A is the Fourier transform of a band-limited signal. B to D are transforms of the corresponding sampled function under the conditions of oversampling, critical sampling, undersampling, respectively. A function f of t whose Fourier transform is 0 for values of frequencies outside a finite interval or band, minus mu max, mu max about the origin is called a band-limited function. Sufficient separation is guaranteed if 1 by delta t is greater than 2 mu max. Sampling theorem. A continuous band-limited function can be recovered completely from a set of its samples if the samples are acquired at a rate exceeding twice the highest frequency content of the function. The Nyquist rate representation is as shown on screen. Aliasing, effect of undersampling a function, transform corrected by frequencies from adjacent periods. Anti-aliasing. The effect of aliasing can be reduced by smoothing the input functions to attenuate its higher frequencies. This has to be done before sampling. Function reconstruction, recovery from sample data. Recovery expressed in the spatial domain is as shown on screen. Image enhancement. To improve the interpretability of the information in images for human viewers, improving images quality by suppressing noise and/or increasing image contrast, sharpening or smoothing images for display analysis, used to improve visual perception of an image. Elementary enhancement techniques are based on histogram. It is a very simple and fast technique. It gives acceptable results. It plays an important role in both spatial and frequency domain. Image enhancement method is divided into two categories. These are spatial domain, transform domain method. Spatial domain method. It operates directly on pixels. Transform domain method. It operates on Fourier transform on image and then it transforms back into spatial domain. Spatial domain. Image processing methods are based on direct manipulation of pixels. The two principles of image processing technique classifications. 1. Intensity transformation methods. 2. Spatial filtering methods. Background. The basics of intensity transformations and spatial filtering. Spatial domain process. G of x, y equals t into f of x, y, wherein G represents the output image, t represents the operator defined over neighborhood of the point, and f of x, y represents the input image. Smallest possible neighborhood. Size 1 into 1, which is t, becomes an intensity or gray level or mapping. Transformation functions S equals T of R, where S equals intensity of G at x, y. Examples: contrast stretching thread holding. Image restoration. Objective process. Recover an image that has been degraded by using a prior knowledge of the degradation phenomenon. Process: modeling the degradation and applying the inverse process to recover the original image, that is, deblurring. Some techniques are best formulated in the spatial domain, that is, additive noise only, others in the frequency domain, that is, deblurring. Image restoration and reconstruction. A model of the image degradation restoration process. Noise models, restoration in the presence of noise only, spatial filtering, periodic noise reduction by frequency domain filtering, estimating the degradation function, inverse filtering, minimum mean square error, Wiener filtering, geometric mean filter. A model of the image degradation and restoration process. If H is a linear position invariant process, is represented on the screen. Spatial domain representation of the degraded image is represented on the screen. Noise models. Principal source of noise during image acquisition and/or transmission. Factors affecting the performance of imaging sensors. Environment conditions during acquisition, that is, light levels and sensor temperature, quality of the sensing elements. Spatial and frequency properties of noise will be assumed to be independent of spatial coordinates, uncorrelated with respect to the image, no correlation between pixel values and the values of noise components. Spatial noise descriptor. Statistical behavior of the intensity values in the noise component. Random variables characterized by a probability density function, PDF. Some important noise probability density functions. The Gaussian normal noise PDF of a Gaussian random variable Z is represented on the screen. The Rayleigh noise equations are also shown. The Erlang gamma noise equations are also shown. Also on the screen, we can see the exponential noise equations are also shown. Uniform noise equations are also shown. And the bipolar impulse noise equations are also shown. Imaging and histogram resulting from adding noise models. Imaging and histograms resulting from adding Gaussian, Rayleigh and gamma noise to the image. Imaging and histograms resulting from adding exponential, uniform salt and pepper noise to the image. Periodic noise typically comes from electrical and electromechanical interference during image acquisition. Can be reduced significantly using frequency domain filtering. Estimation of noise parameters. S subimage, PS, ZI, probability estimates of the intensities of pixel in S, L, the number of possible intensities in the entire image. Restoration in the presence of noise-only spatial filtering. When the only degradation is noise, the corrupted image is represented by the equation shown on screen. When only additive noise is present, spatial filtering. Mean filters, arithmetic mean filter equations are also shown. Geometric mean filter equations are also shown. Harmonic mean filter equations are also shown. Works well for salt noise or Gaussian noise, but fails for pepper noise. Contraharmonic mean filter equations are also shown. Q is the order of the filter, good for salt and pepper noise. Eliminates pepper noise for Q is greater than 0 and salt noise for Q less than 0. Note, CF arithmetic filter if Q equals 0, harmonic mean filter if Q equals -1. Orthostatic filter, median filter equation is shown. This is particularly effective with bipolar and unipolar impulse noises. Max filter. This is useful for finding the brightest points in an image. Equations are also shown. Min filter. Equations are also shown. Midpoint filter. Note, combines order statistics and averaging. Works best for randomly distributed noise such as Gaussian or uniform. Equations are also shown. The alpha-trimmed mean filter equation is shown. GR represents the image G in which d by 2 lowest and d by 2 highest intensity values in the neighborhood S of x, y were deleted. D equals 0, which is the arithmetic mean filter, d equals mn minus 1, which is the median filter. For other values of d, useful when multiple types of noise, combination of salt and pepper and Gaussian noise. Periodic noise reduction by frequency domain filtering. Periodic noise appears as concentrated bursts of energy in the FT at locations corresponding to the frequencies of the periodic interference. Approach: use a selective filter to isolate the noise. Band reject filters, band pass filters. Notch filters reject or pass frequencies in predefined neighborhoods about a center frequency. Estimating the degradation function. Three main ways to estimate the degradation function for use in an image restoration: observation, experimentation, mathematical modeling. Estimation by image observation. The degradation is assumed to be linear and position invariant. Look at a small rectangular section of the image containing sample structures and in which the signal content is strong. That is, high contrast subimage GS of x, y. Process this subimage to arrive at a result as good as possible. Fs cap of x, y. Assuming the effect of noise to be negligible in this area, you get the equation on screen. Deduce the complete degradation function h of u, v, position invariance. Estimation by experimentation. If an equipment similar to the one used to acquire the degraded image is available, find system settings reproducing the most similar degradation as possible. Obtain an impulse response of the degradation by imaging an impulse dot of light, as shown. Ft of an impulse equals constant leading to, as shown. Here, A equals constant describing the strength of the impulse. From the figure, degradation estimation by impulse characterization. A, an impulse of light. B, imaged or degraded pulses. Estimation by modeling. Example 1. Degradation model proposed by Hufnagel and Stanley in 1964 based on the physical characteristics of atmospheric turbulence is shown on the screen. In this figure, A stands for negligible turbulence, B severe turbulence, C mild turbulence, and D low turbulence. Example 2. Derive a mathematical model starting from basic principles. Illustration. Image blurring by uniform linear motion between the image and the sensor during image acquisition. If t is the duration of exposure, the blurred image can be expressed as per the equation shown on screen. If motion in y as well. We can also see the inverse filtering equation on screen. Even if we know h of u, v, we cannot recover the undergraded image exactly because n of u, v is not known. If h has 0 or very small values, the ratio n by h could dominate the estimate. One approach to get around this is to limit the filter frequencies to values near the origin. Figure A is the result of using full filter, B result with full cutoff outside radius with 40, C outside radius 70, and D outside radius 75. Minimum mean square filtering. Objective: find an estimate of the uncorrupted image such that the mean square error between them is minimized. The equation and the assumptions are shown on the screen. Assumptions. Noise and image are uncorrelated. One or the other has 0 mean. The intensity levels in the estimate are a linear function of the levels in the degraded image. The minimum of the error function E is given by the equation shown on screen. When the two spectrums are not known or cannot be estimated, approximation will look like what is shown on the screen, where key is the specified constant. Comparison of inverse and Winter filtering. Geometric mean filter. Generalization of the Wiener filter. The corresponding equations are shown on the screen. Constrained least square filtering. In vector matrix form, G equals HF plus eta. G, F and eta are vectors of dimension mn into 1. H matrix of dimension mn into mn is very large. Issue: sensitivity of H to noise. Optimally, restoration based on a measure of smoothness. Find the minimum of a criterion function C, Laplacian. The equation is as shown. Subject to the constraint, the Euclidean vector norm is also shown on the screen. Frequency domain solution. The equation is as shown, with gamma representing the parameter just so that the constraint is satisfied, P of u, v representing the Fourier transform of the function. The matrix of P of x, y is shown, where gamma equals 0, that is inverse filtering. Goal: find gamma so that mod of G minus H F cap whole squared equals mod of eta whole squared plus or minus A, where A is the accuracy factor. Specify an initial value of gamma. Compute the corresponding residual. Stop if equation is satisfied. Otherwise, if mod of gamma squared is less than mod of eta squared minus A, increase gamma. If mod of gamma squared is greater than mod of eta squared plus A, decrease gamma. Then return to step 2. Adjusting gamma so that the constraint is satisfied, the equations take the form shown on the screen. Adjusting gamma so that constraint is satisfied. Iteratively determine constrained least squares restoration of using correct noise parameters. B. Result obtained with wrong parameters. Piecewise linear transformations functions. Piecewise linear transformations can be arbitrarily complex. Practical implementations of some important transformations can be formulated by piecewise functions. Disadvantage of piecewise function is their specification requires much more user input. In this, piecewise linear transformation functions included contrast stretching, intensity level slicing, bit plane slicing. Contrast stretching expands the range of intensity levels to span the full intensity range of the output devices. Form of transformation function. Low contrast image. Special cases: R1 equals S1, R2 equals S2. Linear transformation, no change in intensity values. Result of contrast stretching. R1 equals R2, S1 equals 0, S2 equals L minus 1, and these are thresholding function, binary image. Result of thresholding function 1, S1 equals M, 0, R2, S2 equals M, L minus 1, where M represents mean intensity level. Intensity level slicing. Highlight or specific range of intensities. Two main approaches. Display in one value, for example white, all values in range of interest and all others in another value, for example black, which is a binary image. This transformation highlights intensity range A, B and reduces all intensity level to lower levels. Brighten or darken the desired range, leaving all other intensity levels unchanged. This transformation highlights all intensity range A, B and preserves all intensity levels. Intensity level slicing based on approaches. Aortic angiogram. Based on approach A, result of using slicing transformation of the type as shown in figure, with the range of intensity of interest selected in upper end of grayscale. Result of using transformation with the selected area set to black so that grays in the area of blood vessels and kidneys are preserved. Bit plane slicing. Pixels are digital numbers composed of bits. Gray level of each pixel in digital images is stored as one or more bytes in a computer. It is a method of representing an image with one or more bits of the byte used for each pixel. Goals of bit slicing. Converting a grayscale image to binary image, representing an image with fewer bits and compressing the image to a smaller size. Enhance the image by focusing, bit plane representation of digital image. For example, 8-bit image 0 is encoded as 0000000 and 255 is encoded as 1111111. Any number between 0 and 255 is encoded as 1 byte. Most significant bit MSB. As shown in figure, the bit on far side is referred to as the most significant bit MSB. Because change in a bit would significantly change the value encoded by the byte, one can use only MSB to represent a pixel, which reduces the gray level image to binary level image. Low significant bit LSB. As shown in the figure, the bit on far right is referred to as a low significant bit LSB, because change in a bit does not change the value encoded by the byte. Some properties of the 2D discrete Fourier transform. Relationships between spatial and frequency domains. If delta t and delta z are the separations between samples, the separations between the corresponding discrete frequency domain variables are delta u equals 1 by m into delta t and delta v equals 1 by n into delta z. Translation and rotation. Translation, it has no effect on magnitude, and the equations are as shown on the screen. Rotation, polar coordinates. F of r, theta plus theta naught, capital F of omega, pi plus theta naught. Periodicity. The 2D Fourier transform and its inverse are infinitely periodic in both directions, and the equations are as shown on screen, where K1 and K2 are images. 1D spectrum. Shift the data so that the origin F0 is located at U0. Please study the equations on screen. If U0 equals m by 2, the equation will be F0 at the center of the interval 0, m minus 1. 2D spectrum. Shift the data so that the origin F0, 0 is at the center of the frequency rectangle defined by 0, m minus 1 and 0, n minus 1. The equation will be as shown on screen. Symmetry properties. Example, if f of x, y is a real function, its Fourier transform is conjugate symmetric, as shown. If f of x, y is imaginary, its Fourier transform is conjugate antisymmetric, as shown on the screen. The table on screen shows the difference between spatial domain and frequency domain. Fourier spectrum and phase angle. The 2D DFT can be expressed in polar form, as shown on screen, where the magnitude will be as shown on the screen. Is called the Fourier or frequency spectrum, and the equation can be seen on the screen. The power spectrum equation is now shown on the screen. R and I are the real and imaginary parts of f of u, v, as shown on screen, where f denotes the average value of f. Mn, usually large, mod of f 0, 0 is typically the largest component of the spectrum. The 2D convolution theorem. 2D circular convolution equations can now be seen. 2D convolution theorem equations can now be seen. And conversely, data from adjacent periods produce wraparound error. Need to append zeros to both functions. In 2D, pad the two image array of size m into n by zeros. Padded images of size p into q, p greater or equal to 2m minus 1 and q greater than equal to 2n minus 1. The summary of 2D discrete Fourier transform properties is given in the table shown on screen. Smoothing spatial filters. Output will be the average of pixels contained in the neighborhood of the filter mask. Averaging filters are low-pass filters. Reduce sharp transitions in intensities, application, noise reduction, smoothing of false contours, blurring effect. The below figure shows that original image of size 500 into 500 pixels, results of smoothing with square average filter masks of size m equals 3, 5, 9, 15 and 35. The general implementation for filtering an m into n image with a weighted averaging filter of size m into n will be as shown on screen. In the below image size 528 by 485 is taken from the Hubble Space Telescope. Image filtered with a 15 into 15 average mask. Result of thresholding of step B. Order statistic nonlinear filters. Ordering or ranking the pixels contained in the image area encompassed by the filter, then replacing the value of the center pixel with the value of ranking result. Median filter replaces the value of a pixel by the median of the intensity values in the neighborhood. Good noise reduction capabilities with less smoothing, that is, impulse noise or salt and pepper noise. X-ray image of circuit board corrupted by salt and pepper noise. Noise reduction with a 3 into 3 averaging mask. Noise reduction with a 3 into 3 median filter. Sharpening spatial filters. Objective: highlight transitions in intensity, spatial or digital differentiation. Enhances edges and other discontinuities. Let's study the behavior of first and second order derivatives in areas of constant intensities at the onset and end of discontinuities and along the intensity ramps. Basic definition of first order derivative of a one-dimensional function f of x is as shown on screen. The second derivative is also shown. Illustration of the first and second derivatives of a 1D digital function represents a section of horizontal intensity profile from an image A and C. Data of points are joined by dashed lines for visualization aid. Using the second derivative for image sharpening, we get the Laplacian discrete formulation of second order derivative, which is the same as a construct filter mask. Isotropic filters. The response independent of the direction of the discontinuities in the image to which the filter is applied, that is the rotation invariant. Simplest isotropic derivative operator, Laplacian, is shown on screen. Laplacian masks. Isotropic result for rotations in increments of 90 degrees. After incorporation of the diagonal directions, isotropic result for rotations in increments of 45 degrees. Negative mask for rotations in increment of 90 degrees, C. Negative mask for rotations in increment of 45 degree, D. Recovering the background. Add or subtract the Laplacian image to the original sharpened image. The equation is as shown on the screen. Blurred image. Blurred image masked using Laplace without scaling and with scaling techniques. Images for result of using mask. Unsharp masking and high boost filtering. Unsharp masking. Blur the original image f of x, y. Subtract the blurred image f of x, y from the original result called mask. The equations are as shown on screen. Add the mask to the original. The equations are as shown on screen. Sharpening and smoothing images. In this image we can distinguish sharpened and unsharpened image. Graph of blurred and unsharp and sharpened signals. Using first-order derivatives for nonlinear image sharpening, gradient of f at x, y equation is as shown on screen. This vector points in the direction of the greatest rate of change of f at location x, y. Magnitude of gradient f is as shown on the screen. M of x comma y with x and y varying over all f is called the gradient image. Note, the gradient is a linear operator but not rotation invariant, isotropic. The magnitude is not linear but is isotropic. Definitions proposed by Roberts in the year 1965 using cross differences. In the below figure, A represents 3 into 3 region of an image with intensity values. B and C represent Robert cross gradient operations. Approximations to Gx and Gy using 3 into 3 neighborhood centered on Z file. In the below image, we can distinguish optical image and Sobel image. Combination of image enhancement method. A. Image of whole body of bone scan. B. Laplacian of A. C. Sharpened image. D. Sobel gradient. E. Sobel image smoothed with 5 into 5 averaging filter. F. Mask image formed from C and E. G. Sharpened image is obtained from an image A and F. H. Final image is obtained from power law transformation.